This graph is from my previous video, nerds83. It is this curve, and it is a little better than the best commercially available low noise oscillator that I have found. It's the NEL1714A, and that's this curve, the red trace. I have had problem with my measurement systems. My UADC4 has failed completely, and now I have a new system. Actually, two systems, one pair of SDR-IP. They run on 10 MHz directly on the signal. And this M-track quad, which runs on the audio signal from my 2-channel receiver. It looks complicated, and actually it is pretty complex. Here is the schematic diagram. The heart of the system is two good 10 MHz oscillators, one here and one here. They are phase locked, but with a very low time constant. So they don't share sideband noise at frequencies above something like 0.1 Hertz. These local oscillators drive Schottky mixers, two of them in quadrature, and then there is an input signal from here that is split into two channels, one here for one oscillator and the other one here for the other oscillator. And the output from the mixers is amplified and run into the M-track quad. And at the same time I take out this reference signal from one oscillator and from the other oscillator to use as references for the SDR-IP units. So they are locked to 10 MHz, but they don't share the low frequency noise from these reference oscillators. Not until the frequency is below 0.1 Hertz or something like that. And then I have couplers to take a part of that signal that goes this way to put into the SDR-IP units. So that is the measurement system that I'm using now. Here is the sound card, and here is the pair of SDR-IP units. They have been running for 28.5 hours now, both of them, and they show a similar result. At 2 kHz here, that's 182 dBc per hertz minus, and here 2 kHz minus 183 perhaps. Anyway, the result is not reliable. The correlation gain from here all the way down here is rather big, and there could be problems with the setup. And that is clear here. You see these blue regions. That means that the signal is in antiphase, which is not the noise of the oscillator. And I don't know what it is. Maybe it's the spurs in the SDR-IP units. And further, the red dots are at the same level, and that is the signal in quadrature, the signal that is 90 degrees from the expected noise of the amplifier. So this setup shows that my system is not capable of measuring better than about minus 180 up here somewhere, maybe even 78. And it's the same for both systems, although I don't see as many blue regions for the sound card. I have set now the systems for a bandwidth in the order of 5 Hertz. From here to here is 10 Hertz, and this is a little bit narrower, maybe 8 Hertz or so. And that makes it not possible to study what happens at very close range. I have set a much larger sampling speed for the baseband, the highest I can get with the current version of Leanrod, and I reset now. Like this, and you can see how the average goes down slowly, or actually not so slowly. There are already 600 averages here and 400 here. And I will allow this to run for a while to see when it reaches 184 or thereabouts. After 6 minutes, I see here with the SDR IP at 15 kilohertz, something like this, and that is minus 180. And with the M audio at minus at this 6 minutes, 6.5 actually, and 15 kilohertz, I see minus 176. That reflects the lower dynamic range of the sound card system at 15 kilohertz. The uncorrelated spectrum is at minus 150, while it is at minus 154 with the SDR IP. So after 1 hour, that's 10 times more, I should see about 4 or 5 decibels lower if I don't have any artifacts in the systems. 1 hour and 15 minutes. The SDR IP has improved by about 2 decibels. Now minus 182 at 15 kilohertz, while the sound card at 15 kilohertz is about minus 179, and that is a 3 decibels improvement for about 4 times more time. So it seems I'm reaching some kind of limit with the SDR IP, while the sound card still can go a little bit further down. After nearly 4 hours, the SDR IP seems to converge towards minus 182 dBc per hertz, and the imaginary part is significantly below the yellow trace. On the sound card, the result is similar, close to minus 182, but there is a spur which comes negative in the real part, and the imaginary part is not well below the yellow. But maybe it will go down. I will see tomorrow. 50 hours. The SDR IP gives a flat curve here at 182 or 181.1. And the imaginary part is well below, around minus 192. It seems that with this long measurement time I could make reasonably reliable measurements down to maybe 188 or so. But with the sound card the situation is different. This is the same statistics roughly, and the uncorrelated curve is only about 2 decibels higher, but I can see here this is curved. Here the points or the curve is blue, which means that the sign is negative. At some point here it is infinitely deep, yellow or blue. So this is some correlated signal that shouldn't be there and that affects reliability. And it's the same here. There are spurs, not very strong, but of the wrong sign. and here is a big one with the wrong sign. So the sound card is not useful for low sideband noise levels at frequency offsets in the order of a kilohertz or more. I have increased the sampling rate of the sound card, the M-Truck Quad, from 44.1 kilohertz to 96 kilohertz. And obviously the noise floor is much better now. It competes reasonably well with the SDR-IP. So I will wait for a while and look at the presence of spurs with negative sign. The sound card has been running for 18 hours now, and I can see it is not flat in the same way as the SDR-IP pair is. It's running up to 20 kilohertz here. There are some little spurs, but nothing very strong until I come down to about 3 kilohertz here. And it's been running for 70 hours now. So something is incorrect here, and the strongest feature that shouldn't be in place is this spur. The frequency is 12 kilohertz, and when I look at the spectrum, I see this line, pretty strong one, at 12 kilohertz. And then I see here, with the 4 kilohertz separation, there has to be one in between here and one here that I don't see in the waterfall. But when looking at this graph, from here to here is about 4 kilohertz. Here is something going negative, a spur, 4 kilohertz below, and here at 4 kilohertz I have some structure. So something is at 4 kilohertz. I can look at the amplitude spectrum here. And it has this 12 kilohertz spur and not so much the other ones. I can also have a look at the amplitude noise with the SDR-IP units, and it looks very similar to the phase noise at high offsets, but coming close to the carrier it is more noisy, and that's natural because there is AM noise in the SDR IPs. I can bring the curve down, and here you can see more clearly why it goes up, because the AM noise of the receivers themselves becomes very high here. I can look at the spurs in normal processing mode without correlation. The strongest one is at 24 kilohertz. So I look at it with high resolution in the baseband, and then I can see there are actually 4 signals there, which explains why it looks so ugly when I look at the sideband noise. It is the same in both channels, which you can see here. I will switch off the signal and see whether it is modulation on the signal or whether it is plain something in the sound card. There is no strong signal present anymore, but the spurs didn't change when I switched off the signal into the receive system. And the noise floor or the signal levels, it didn't change noticeably. So remains to see whether this signal comes from inside the sound card or from my receive system. Here I added 4 50 ohm dummy loads on the inputs to the M-track quad, and here I can see there is no change at all. So it is an internal problem of the sound card. Here is a magnetic field sensor, several turns on thin wire on a small ferrite rod. I look at the lean rod screen while putting that sensor at various places inside the sound card. And as you can see, on the screen, various places, like here for example, gives this pattern. Here, very similar. This chip is a USB hub. This is a multiplexer. Here is an oscillator. And this one is labeled 12 megahertz. But I see all the frequencies everywhere. And on top of the AD converters here, not very strong. And even further out, well, there are many crystal oscillators inside here, here and here and here and here. 4 of them. And everything is far too complicated, so I do not want to try to modify the digital parts here. So I have to live with these spurs. I have set a very narrow bandwidth for the filter from which I extract the carrier for the quadrature detection I am using to get phase modulation and AM modulation. It is obvious that the data I get is not okay below about 0.3 Hertz. That's here with the sound card. And with the SDR IP pair, it's about the same, maybe 0.4 Hertz. Now, the signal is not far above the imaginary part, which represents the noise level. I can read at about 1 Hertz minus 124 dBc per Hertz. And for the sound card at 1 Hertz, that's here, I can read also minus 124, but with a much better statistic accuracy. So I can use the SDR IP at wide separations and the sound card at narrow separations. At 5 Hertz I can see minus 143 with the sound card, and I don't know what will happen at higher offsets. I have set the parameters for the sound card now to get rapid results at about 5 Hertz offset. The baseband filter here is about 1 Hertz wide, so I cannot read at 1 Hertz offset, I think. Maybe, we will see. But at 5 Hz I have already 143 after 1 minute. Minus 124 at 1 Hz. 124. It's here. It's about 3 decibels a degradation compared to what I've seen before with this unit. And at 5 Hz, minus 143, that's here. That's 4 decibels worse. Now, it isn't the same unit anymore. I made some modifications to test various things, and then my UADC4 failed. But now I have the tools so I can start to look at the modifications of the oscillator again, although not as easily as before. I have set parameters for the sound card. 5 Hz minus 143, that is 38 minutes. And here also 38 minutes. At 10 kilohertz it shows minus 180. I expect minus 182, so that will take maybe 4 times as long. That's 2 hours. It's not an hopeless time to wait. One of the modifications I made was to put 2 crossed Schottky diodes from here to ground. That reduces the signal level that goes to the input and limits the power of the oscillator. The output level has been 2 volts peak to peak. That's 10 milliwatts into 50 ohms. There is this 50 ohm input. And here is what the unit looks like. These extra diodes there that are crossed across the 2 series connected pairs of 1N 4148. I will just remove those diodes now. And now the level is 5.4 volts. The power level is then 6 times higher. That means 8 decibels. So the expected 182 should go down to minus 190. That is probably below what I can see here tomorrow after a couple of hours. Here the close range already after 1.5 minutes at 5 Hz. I can guess it is still minus 143. It will not take a very long time to see what happened there, but I will not wait for it this evening. This is 9 hours. The noise floor at 5 or 10 kilohertz is now maybe minus 186. It has not reached the proper value. That will take much more time probably, and I will not wait for that. I had set the strIP instance of Linrod to elevated priority. That caused the sound card instance to stop working. It just froze. So when I came back, it didn't show any reasonable result. Now that was 1 hour ago. It has now been running 1 hour, 4 minutes. And that is enough to get a good reading at 5 Hz. So 5 Hz, it is here. And what I see is minus 142. So I have lost 1 decibel by increasing power like this, while I have gained maybe 8 decibels on the wide range. That is not a good compromise. I want the close range much more than the wide range. I will now try to restore the previous very good result. and I have forgotten exactly what changes I did, so this will take some time, and I will not record all of what I'm doing as videos. So I stop this now, and hopefully I will come back with something that is as good as Nerds 80 or even better.